So today we have Yi-Nan Wang tell us about 5D and 6D SCFTs from 3D orbifolds. Take it away.
Yeah. Thanks, Julius, for the invitation and introduction. So I'm pretty happy to give a talk again at this Quiver meeting, although I have to do this online now. So I'm going to talk about this new paper with Jiahua Tian, who's currently a postdoc at ICTP, on the construction of 5D and 6D 1,0 SCFTs from C3 orbifolds. The structure of this talk is like this. First, I'm going to shortly introduce the physical motivation of this work. And then I'm going to briefly reveal a very nice mathematical subject, which is called the 3D Mckay correspondence of C3 mod gamma orbifold. And then I'm going to present the dictionary between the 5D SCFT constructed from M theory on this orbifold singularity and the group theoretic data of this finite group gamma. And then I'm also going to discuss the construction of 6D SCFTs from the same singularity, but embedded in an elliptic Clapeyron threefold model. So this only happens in certain cases, but it's not always possible. Finally, I'm going to present more detailed examples and to discuss their physics. Okay. And so the first thing is a physical motivation. So as we know, roughly speaking, there are two different ways to construct 5D n equals 1 ICFTs in the framework of string M theory. The first thing is to put the 11-dimensional M theory on a canonical threefold singularity we call X. And so on the geometric picture on the left, so in this picture, we just have a singularity as the origin, and we don't have any scale parameter in this geometry. So these are the the extra dimensional geometry. Then if you consider this dimensional reduction to 5D, and physically this corresponds to the fact that the 5D field theory will not have any mass scales, such that we get a superconformal theory. And then we can consider the smoothing, or for example, the resolution of the singularity X, and to get the picture on the right. So physically, this corresponds to going to the Coulomb branch of the 5D SCFT. And here I just present, so I will not reveal all the literature on this subject, I just present a very incomplete list of authors on this subject, okay? So I'm going to say a few more sentences just to reveal the basic geometry versus physics dictionary in this approach. So consider the resolved Clapeyron threefold with various compact cycles and non-compact cycles as well. Firstly, each compact exceptional 4 cycle that we call SI, so they one-to-one correspond to the U1 gauge field on the 5D Coulomb branch. And in particular, the total number of these SIs is equal to the rank, little r, of the 5D SCFT. Furthermore, there are also a number of non-compact 4 cycles we call d alpha, whose number give rise to the rank of the flavor symmetry GF of the 5D theory. And we call this flavor rank little f. Okay. Now, besides the 4 cycles, we also have a bunch of 2 cycles in the resolved geometry, where we can wrap M2 brane over them to get 5D like vector or hypermultiplets depending on the normal bundle of C. And as another important ingredient of the effective theory on the Coulomb branch, so the prepotential function can be derived from the triple intersection numbers of these exceptional 4 cycles in the geometry. And besides this information about the Coulomb branch, you may also wonder how do we study the Higgs branch of the 5D theory in general in this geometric picture. But up to now, this is not a well-studied subject, and we can only study the Higgs branch nicely in certain subclasses of canonical threefold singularity. Okay, and I will say a few more words about this in the like 2 slides after. And besides the geometric engineering approach, we also have a very powerful string theoretic construction called type 2B brainweb approach. So again, I just list, so this is a very incomplete list of authors on the subject. So the power of this type of construction is that one can easily study both the Coulomb branch and Higgs branch in this way. Nonetheless, this kind of approach also has its own limit, because up to now, there's still not a well-defined map from the singularity in the previous approach to a brainweb. For example, if you just take an arbitrary like generic terminal singularity, or these exotic cases of singularity where after the resolution, you get a bunch of singular divisors. So I think up to my knowledge, there's still not a good way to really write down what are the brainweb picture of these singularities. Okay. So in this talk, I will focus on the first approach, which is the geometric engineering in M theory. And here, this is a very short review of the current progress on this subject. So although mathematically, there's still not a complete classification of the canonical threefold singularity, but we have already studied various different subclasses of this geometry. So for example, for the simplest examples are the toric threefold, where we can easily study both the Coulomb branch and Higgs branch. This is basically just because the corresponding brainweb picture of toric threefold is can be very easily defined. And besides that, there's also a very big class of singularities that come from the non-isolated elliptic singularities. And because if we want a 5D model instead of a 61, so actually we have to do a non-flat resolution of these elliptic models. And because for here, these singularities are non-isolated, so it's very hard to study the deformation of these singularities, and we could only study the Coulomb branch in a nice way. Besides that, in a recent series of papers with zero closure and subsurface trigonometry, we have studied the isolated hypersurface singularities, which take the form of a hypersurface equations in 4 complex variables, so in C4. And in this case, because the singularities are isolated, then the deformation series are well defined, such that we can study both their Coulomb branch and Higgs branch. And now, so in this talk, I'm going to present another big subclass of singularities that are the C3 orbifolds. So that was studied both in our paper and also a paper by Bobby Acharya, Neil Lambert, Marvin Najar, Eric Spanis, and Tian, actually one day before our paper. And in this case, because generically the C3 orbifolds are also non-isolated, so most of them are non-isolated, and we are only focusing on their Coulomb branch property as well. Okay, so that was a brief introduction. So now, in the following part of this talk, I'm going to focus on the C3 mod gamma orbifold, where gamma is a finite subgroup of SU3. So this is required because we want this thing to have a SU3 holonomy, and also after a preprint resolution, we want to get a Clapeyron threefold to preserve supersymmetry. So now one question is, why do we want to study this particular class of singularities? Is there any nice mathematical structure to simplify the computation? So the answer is yes. So there's a very nice mathematical notion or philosophy called the Mckay correspondence. So here I just present the rough philosophy of Mckay correspondence in a general n dimensions. So let's consider a finite subgroup gamma of SLN. And then there are two different one-to-one correspondence between a group theoretic object and a geometric object in the resolved Clapeyron n-fold x tilde of this orbifold singularity. So the first rough statement is that the different conjugacy classes GI of gamma is one-to-one correspond to a topological cycle CI in the resolved Clapeyron n-fold. And the second correspondence is about the representation of the gamma, which says that each irreducible representation, so there are a finite number of them as a finite group, the rho I is one-to-one correspond to a certain vector bundle on x tilde. So before I'm going to the main subject with the 3D Mckay correspondence that's relevant in our subject, I'm going to first reveal the basics about the 2D Mckay correspondence because that's a more well-known one. Okay. So in the 2D Mckay correspondence, hi, Ami.
Yeah. Hi. Yeah. I think that's too simplistic. Is it? This is the perspective of 3D 97. There are just too many cycles and not that many conjugacy classes.
So that's a generator of the Cho group. These are the generators, like including generator of the Picard group and also the group of 2 cycles.
Yeah, I would say even for 2 dimensions it would work fine. For 3 dimensions we'll start having issues. For 4 dimensions, just a mess. It's too simplistic. I don't know if you already noticed this, but it's not an easy correspondence.
Yeah. So to my knowledge, I think in 3 dimensions this is still correct, but maybe for the higher dimensional cases there are more subtleties. So I haven't looked at the 4D Mckay correspondence. So I know you and Yang Hui He has been writing papers about 20 years ago about this subject. So maybe you know more about it.
Yeah, and they were extracting the terms of the superpotential is quite a challenge, right? So but that has to do with some gauge theory. Yeah, I think these points 1 and 2.
Yeah.
Just too simplistic. But anyhow, I don't know if you are going to what of this you're going to use. I just want
yeah. Actually, not too much. It's like,
I see. Okay.
Yeah.
Okay.
So I'm only going to use some basics. Yeah.
Can I just ask, what is the status of this? I thought it was a theorem. Is it not proven?
No. Not proven for the general n dimensions.
I see. So that's why I said.
Yeah.
So it's proven in 2 dimensions, and then it's just a conjecture in higher dimensions.
In 3 dimensions, also kind of proven. Yeah, certain versions are proven.
I see. Okay.
They keep on meeting every 2 years. That's you know about this, Antoine. Right? The group of Reed keeps on working on this 3D Mckay correspondence, and they have biannual meetings.
Okay.
Yeah, the progress is quite slow.
Yeah.
Anyhow,
yeah. That's why I say that these are just some rough philosophy and conjectures. Yeah. So, okay. So now about the 2D Mckay correspondence. So this is just a C2 model gamma ADE, where so this is just a Kleinian singularity, and the gamma ADE are a finite subgroup of SU2 that classified by the ADE Dinkin diagram. So now let's apply the first sentence of Mckay correspondence. And so for each non-trivial conjugacy class G, that's 1-to-1 correspond to an exceptional P1 curve in the resolved Clapeyron twofold, which is actually in this case an ALE space X2. So the intersection pattern of this P1 curve exactly forms the AD Dinkin diagram, as we know. Nonetheless, there's a less known version of this Mckay correspondence, which says that one can recover the same AD Dinkin diagram just from the group theoretic structure of gamma ADE. So one could just try to look at the maximal abelian subgroup of gamma ADE, and you can draw some some Quiver diagram and group them together, and after that you get the AD Dinkin diagram in a different way. So let me show an example of this particular Mckay correspondence that I just said. And so let's take the binary dihedral group which I call the D4. So that's labeled by the Dinkin diagram D4. This is actually a group with 8 elements, and it's generated by the 2 matrices A and B. So there are 4 different non-trivial conjugacy classes that are labeled by their element, representative element, a times b, and -1 times the identity matrix. And there are also 3 other elements, a cube, b cube, and ab cube, and a and a cube are in the same conjugacy class, and so on. So now let's write down the figure out the maximal abelian subgroup of this non-abelian binary dihedral group. So in fact, it turns out that there are 3 Z4 subgroups that can be drawn in this way. So here I ignored so I just omitted the trivial element and just write down. So there's a Z4 subgroup generated by the element A, because A has order 4. So it's a squared, a cube, and so on. So in this picture, I colored a different node depending on whether they are in the same conjugacy class or not. So if they are in the same conjugacy class, then they are colored with the same color, like the red one. And in particular, for the white nodes, so a squared, b squared, and ab squared, they all equals to -1 times the identity matrix. So they are actually identified. Okay. So now we can glue these 3 pictures together by identifying the nodes with the same color. And as a consequence, you get exactly the D4 thinking diagram as we know. Okay. So this was the conjugacy class version of the 2D Mckay correspondence. There's also the representation version of the 2D Mckay correspondence, which is formulated in a different way. So now let's consider the tensor product decomposition of an arbitrary E-rep rho I with a pi. So pi is a natural 2D representation of gamma. And we do the tensor product decomposition to get a direct sum of a number of E-reps, rho j. And there are some non-zero coefficient aij over here. Okay. So from this decomposition, we define the Mckay quiver like this. So in this quiver diagram, each node I will correspond to the E-rep rho I. And then for each non-zero aij, we draw aij arrows from I to j. Okay. And then after you do that for every finite subgroup of SU2, the Mckay quiver you construct are exactly has a shape of a finite AD thinking diagram, depending on which type of the AD subgroup it is. Okay. And another pretty nice fact is that the affine node that labeled by the white node is always correspond to the trivial representation of this finite subgroup. Okay. So that was the pretty well-known, I think, 2D Mckay correspondence. So now let's go into the main subject with the 3D Mckay correspondence. So of course, unlike the 2D version, so the number of finite subgroup of SU3, there's just too many possibilities, and there's not a very nice correspondence between the subgroups of SU3 and some sort of Lie algebra. However, we can still formulate the version 1 of the 3D Mckay correspondence using the conjugacy classes G. So now, because for every element in a particular conjugacy class G, all of these elements can be simultaneously diagonalized. So basically, for this G, all of these elements has the same eigenvalues like written in this form. And in the following part of this talk, I will use a shorter notation, like this one is just defined to be something called like 1 over R times ABC, in order to simplify the notation. Okay. And we require that ABC actually lies in the range, so they are non-negative integers, but they are not equal to the little r here. Okay. So now, because of the fact that gamma is a finite subgroup of SU3, which means that the determinant of every element equals to 1. Okay. So this means that if we define a so-called H function of a conjugacy class or each element of the conjugacy class G, that's defined in this way, Hg equals to 1 over R times A plus B plus C, So because each of these 3 by 3 matrix has a determinant equals to 1, it means that the h function is always an integer. And also because of this range we define here, and this h function can only take the value of either 0, 1, or 2. So it cannot equals to 3 or a bigger integer. Okay. So it's just because of this. So now let's define the set of different conjugacy classes G with a particular age M to be the set we call gamma little m here. Okay. So this is a set of different conjugacy classes. So now let's formulate this 3D Mckay correspondence following a paper by Ito and Reed in 1994. So for each conjugacy class with age equals to 1, that's 1-to-1 correspond to a compact 2 cycle in the resolved Calabi-Yau threefold X tilde. And then for each conjugacy class with age equals to 2, that's 1-to-1 correspond to a compact 4 cycle in X tilde. And finally, there's also another nice thing that X tilde has no 3 cycles and there's no terminal singularities after the resolution either. So these are all pretty nice geometric properties of X tilde. Okay.
What about age 0?
Age 0, that corresponds to the trivial conjugacy class of the identity element.
Awesome.
No. Okay, so let's reformulate the statement of the 3D Mckay correspondence in the language of 5D SCFTs, defined as M3 on the C3 mod gamma orbifold singularity. And we consider the resolution of the C3 mod gamma into X tilde, such that we go to the Coulomb branch. Well, the first statement is that because for each conjugacy class G in gamma 2, that corresponds to a compact 4 cycles SI, then we just have a very simple equation, is that we can compute the rank of the 5D SCFT simply by counting the number of conjugacy classes with age function equals to 2. So this is actually pretty powerful because it means that if you want to know the 5D rank, we don't need to do any resolution or anything like that. We just need to compute some group theoretic data. Yeah. And secondly, for each conjugacy class in the set gamma 2, let's consider its inverse conjugacy class that we call G minus 1. And so the elements of G minus 1 are the inverse element, are the inverse of the elements in G. So basically, if you take any conjugacy class, you take the inverse of every element, and the set of this inverse element also form a conjugacy class. That's the G minus 1. Okay, and because of the definition of the H function, this inverse conjugacy class will have an H function equals to 1. So that's an element of a gamma 1. And in fact, geometrically, this guy, should correspond to a 2 cycle in the resolved geometry. And this 2 cycle is exactly the Poincare dual of the 4 cycle that corresponds to the G in gamma 2. So now imagine that you have already done all the pairings like this. You take a conjugacy class in gamma 2, you pair it with an inverse conjugacy class in gamma 1. But in most of the cases, it turns out that there are still some remaining conjugacy classes in gamma 1 that's not paired in this way. And we call these guys, so the set of these guys are gamma 1f, little f. And these guys geometrically will exactly correspond to the flavor curves that give rise to the flavor symmetry of the 5D SCFT. Okay, so basically, if you want to compute the flavor rank of a 5D SCFT constructed in this way, you only need to take take these 2 sets and compute their orders and take the difference, and you just get the answer. This is another pretty nice thing. Okay. So now you may wonder about how about the detailed global symmetry of this 5D SCFT, which includes both the ordinary 0 form symmetry and the higher form symmetries. So in fact, it turns out that the zero form symmetry is a little bit hard to study. Hi, Ami.
Yes, I have a question about the simplest example where you have a flavor symmetry. What is the simplest group?
Sorry?
I guess it should be non-abelian. With,
You mean the group gamma?
Yeah.
Well, the simplest example is like gamma equal to Zn times Cn, just the Tn theory.
And what about the non-abelian? Did you look at delta 27?
Yes, we have already studied that. Yes, so that's a rank 1 cyber V8. Yeah.
I see. Right. Okay.
So I will talk about some examples in the later part of this talk.
Okay.
Including the case that you asked. Yeah.
Okay. Thank you.
Okay. So actually, instead of computing the zero form symmetry, so actually, the one form symmetry turns out to be can be pretty easily computed from the group theoretic data of gamma using the Mckay quiver in the 3D version. So in fact, today I also learned that there is a new paper by Michele Del Zotto, Jonathan Heckman as your students, where they also computed the two form symmetry in these classes of models as well. Okay, but I will just focusing on the electric one form symmetry of these things. And then, whenever the C3 mod gamma is non-isolated, then for the codimension 2 singularities, the ADE type of these codimension 2 singularities can be resolved by the maximal Dn, Dn, or En subgroups of gamma. So here, these guys just means some finite subgroups of SU2. Nonetheless, as I will discuss later, these guys will not really give you exactly what is the actual flavor symmetry group GF. So this is still a unsolved question. So in principle, you still have to do the resolution if you want to learn about this. Finally, for the triple intersection numbers, which is a crucial physical data, there's no easy way to compute them without doing resolution either. So I will not talk about them in the Mckay correspondence section. Okay.
So are there examples of isolated singularities that nevertheless have a non-zero flavor rank?
Well, in general, sure. I mean, this was a paper by me and Cyril Closet and Sakura. So we have studied a lot of these examples. So in the case of this orbifold singularity, I think, let me think, probably not easy to find this example in this particular class, but in general, yes.
Okay, thanks.
No, not to my knowledge in this C3 mod gamma class. Okay, so now let's expand in a little bit more detail about the point 3 and point 4 before we go into the examples. And for the one form symmetry, so here I just briefly review the computation of the electric one form symmetry in this type of M-theory construction. But that was already worked out by Dave Morrison, Sakura, and Brian Willett 1 or 2 years ago. But the idea is just that, just imagine in the beginning we have a pure U1 to the R gauge theory, which has a U1 to the R one form symmetry. Nonetheless, this U1 to the R is broken to a subgroup, that's the gamma E1 electric, by certain M2 brane wrapping modes over 2 cycles in the result Clapeyron threefold. And the electric charge of this M2 brane wrapping modes under a particular U1J can be computed using this intersection number computation, the Ci.Sj. And basically, after this breaking, the residual one-form symmetry is given by this quotient form, which is ZR multiplied by the curly M times ZR plus F, where curly M is a intersection matrix between the 2 cycles and 4 cycles in the resolved Clapeyron threefold. So in practice, one can do the symmetric composition of curly M in this form, where the matrix D is a Smith normal form of curly M. And after you have already put this D in this form, we can simply read out the one-form symmetry as a quotient group pretty easily. So now you may wonder, in this particular class of C3 orbifold singularity, how do we compute this one-form symmetry in an easy way? So it turns out that we can apply a particular version of a 3D Mckay correspondence that is proposed by Ito, Ikari, and Nakajima in 2000, which is formally proved by Bridgeland, King, and Reed, which roughly speaking, for every gamma, one can construct a unique irreducible Peking resolution as a so-called gamma Hilbert scheme. I will not talk about this detailed definition of this thing, but the important thing for our purpose is that we can apply a corollary which helps you to compute the one-form symmetry of the physical theory. So now let's take the Mckay quiver in the 3D version defined similarly in this way. So here pi is a natural 3D representation of the gamma, and rho i's, rho j's are different E-rep of gamma. And now from the coefficient Aij or Aji here, let's define the anti-symmetrized adjacency matrix A gamma in this way. So each matrix element big Aij equals to the anti-symmetrized this thing. Okay. So now the statement is the A gamma, this big matrix, has the same Smith normal form as the extended intersection matrix, which has a dimension 1 plus B2 plus B4 times 1 plus B2 plus B4 that we call M gamma. So basically here, each column and row represent a different topological cycles. So for example, this is a 0 cycle, these are the 2 cycles, and these are the 4 cycles, and so on. So basically, after you define this, you can only get a non-zero value when you take the intersection product between the 2 cycle and the 4 cycle. So that's why these 2 blocks are the only non-zero components. Okay. So the point here is just to make the dimension of these two matrices match, because this big Aij matrix that come from the little Aij matrix also has a dimension like this. Okay. And so basically, the procedure of computing one-form symmetry is like this. Let's just take an arbitrary finite group gamma, let's compute the tensor product decomposition and all the coefficient Aij here. Let's draw the Mckay quiver and compute this matrix big Aij, and then compute the Smith normal form. And from that, we can just directly deduce what is a one-form symmetry of the 5D SCFT defined on this singularity. Okay. So this is a bit abstract, and I've just shown an example, which is a gamma equals to, this is a pretty simple abelian case, gamma equals to D5, whose generator is given in this form using the previous notation. So here the Mckay quiver is like a pentagon, like this. This is a pretty nice picture. And from this Mckay quiver, we compute the anti-symmetrized adjacency matrix big Aij, which takes the following form. So this is anti-symmetric 5 by 5 matrix. Okay. And then we compute the Smith normal form of this guy, which exactly takes this form, this diagonal form. And because these diagonal numbers are basically the double copy of the Smith normal form of a curly intersection matrix M. And because of that, we can directly reduce the electric one-form symmetry of this theory to be D5 because of the 5 over here. And in fact, for this abelian case, it also has a toric geometry description like this. And you could verify this computation geometrically pretty easily. So is there any questions?
Yeah, so there is no clear gauge theory description for this singularity, right?
No 5D gauge theory description.
Yeah, there were only 3 external legs, and that's a kind of like the E0 family. But, yeah. Okay.
Yeah. Okay. So then that was a one-form symmetry. So I will just comment a little bit on the computation of zero-form symmetry, which turns out to be pretty hard. So in principle, when you have a non-isolated singularity, then the way to compute the zero-form Fourier symmetry is by resolving these codimension 2 singularities, and such that you get a bunch of non-compact divisors, and from that you can deduce the Fourier symmetry GF, maybe. In this paper, we give this actually a conjecture, is that the codimension 2 AD type of the C3 mod gamma is given by the maximal Cn, Dn, or En subgroups of gamma. So these are precisely corresponding to like An, type An, Dn, and En codimension 2 singularity. Nonetheless, it turns out that this codimension 2 ADE type is not sufficient to determine what is the actual Fourier symmetry GF, which so the GF should be computed from a very complicated triple intersection number computation, like these kind of things. And so roughly speaking, there are 3 different reasons that we can understand. The first reason is that, if you go from the Calabi-Yau 2-fold to Calabi-Yau 3-fold, then even if you have a codimension 2 ADE singularity, there could be some kind of monogamy reduction effect that's analogous to the monogamy reduction in the F-theory. So you, for example, you start with some kind of A-type singularity, and it's reduced to a non-simply laced Fourier symmetry group like SP. But in many detailed cases that we have looked at, it's even more complicated than that. So for example, we have this kind of situation that is so-called degeneration flavor curve. So in this geometric picture, imagine that we have a type like A1 codimension 2 singularity, and after we resolve it, we get a non-compact divisor that's we call D. And then there are a family of compact divisors labeled by ST, such that for a generic value of T, the ST and D intersect at a -2 curve, which should give rise to a SU2 Fourier symmetry. However, it turns out that for the actual, the compact exceptional divisor S0 in the resolution, this guy will intersect D at this degenerate locus, which consists of 2 -1 curve. And whenever this happens, it turns out that the actual 5D flavor symmetry should be reduced to U1 rather than SU2. So this is a very peculiar effect in the 5D SCFT. And thirdly, there's also could be some additional Fourier symmetry enhancement, as in the simple example of 5D T3 theory that given by this non-isolated, actually it's an orbifold singularity as well. So here, you can read off 3 copies of SU3 Fourier symmetry from these codimension 2A2 singularities. However, as we know, T3 series just is the same as a rank 1 Seiberg E6 theory, and eventually the Fourier symmetry should be enhanced to a bigger group E6. And we cannot detect this easily using the geometric method. Okay. So that was a dictionary between the finite group gamma, and the 5D SCFT. So now what about the 6D SCFT that I also introduced in the beginning? And so this only happens in some of the cases, but not every case. So suppose that after we write down the form, an equation of the orbifold singularity, and suppose that it can be written as this equation, in 4 complex variables, x, y, z, and w. And this just looks like an elliptic model, it's a cubic equation in the variables x and y. And whenever this happens, this system gamma singularity can be embedded into an elliptic model that we call x elliptic, which takes the form of this equation. So this is very similar to the previous equation, and the only difference is that the x, y, and big Z are now the projective coordinates of a P231. So this is an elliptic model. So now, from F3 on the elliptic model, we can define a 60 SCFT T60. And of course, for M3 on the original singularity X, we can also define a 50 SCFT T50. So you may wonder, what are the relations between T60 and T50? So it turns out that the relation is different depending on whether the 60 theory is very fixable or not. So now I will review a little bit about the 61,0 SCFTs and the notion of this very fixable. And so as we know, the lot of known 61,0 SCFTs can be classified by their tensor branch geometry, where we have an elliptic fibration over a base B2, and the fibration is flat. And that was already done a few years ago. And now we consider, the blow down of B2 by, blow down all the -1 curves recursively, and we get some kind of base 2 fold that we call B. And then this 60 SCFT is defined to be very fixable if the B has no compact curve, and in a simpler word, B is just equal to C2. So the examples include, the simple rank 1 E string or rank 1 N E string, and also many other examples as well. If that doesn't happen, and if on the other hand, if there are still remaining compact curves on the base B, and this curve has to be, has self-intersection number -2 or lower, then this case is called a non-very fixable theory. An example will be if you have a non-abelian gauge group G on a -2 curve. Okay.
Yi-Nan,
Hi.
from the gauge theory point of view, there is a residual gauge symmetry which is left unbroken. So, and I guess that's also the reason for the name fixable. Now, what happens in the gauge theory when you have this distinction between the
you mean a gauge group on these curves?
Yeah, because as far as I know, minus two curves are
sure.
Okay, so what is the from the gauge theory perspective? What's the difference between those two?
Even if you have a gauge group on these curves, this is still called a very fixable series. So I think this name only care about the base property, but not the gauge groups. That was the terminology that they invented before.
What these guys?
Yeah.
They're supposed to know gauge theories. So why are they using this? Why are they using this terminology?
I don't know, but this seems to be just a property of a tensor branch, of a tensor multiplet.
Okay, but in both cases, the gauge group is completely broken.
Broken when you go to the origin of tensor branch or what?
Well, if you go to the origin of the tensor branch, you lose the gauge theory interpretation. But
Yeah,
let's say
yeah.
you
There's
have
no, there's no Lagrangian description. You get SCFT, yes.
So, but let's say you are going along in terms of range away from the origin, then
Yeah.
there is some low energy gauge theory, and you could ask the question whether there is complete Higgsing or not. That's the way I would understand it. And from this name,
Yeah.
I gather that in both cases you have complete Higgsing, because they call it Higgsable. And
Yeah, yes, exactly. There's not too much difference in terms of the Higgs branch of the 60 series. So this is a property of the tensor branch.
yeah, but even when you are not in the Higgs branch, you could ask the question whether the gauge group is fully broken or not. But are you saying the difference between very Higgsable and non-very Higgsable is the existence of a -2 curve?
The -2 curve after you blow down all the -1 curves.
I see.
Yeah.
Okay.
Okay.
Sorry, can you hear me?
Yeah.
Yeah.
The difference, I think, is that very Higgsable theory is completely Higgsable to free hypers.
Yes.
Whereas the non-very Higgsable theory can be completely Higgs to a 2,0 theory.
Yes.
2,0.
Yeah.
I see. Okay.
And so the case 25 doesn't have any gauge group in this case, but you can have very Higgsable theories with gauge groups as well. But those can be completely broken in the Higgs branch.
Yeah. So. Yeah.
Wait. Wait, Fabio. So let's take the example of a single -3 curve with a non-Higgsable SU3 on it. Then you cannot break it.
Right. Indeed, it's a non-Higgsable theory.
Yeah.
So is
But
there
that's not, that cannot go to a 2,0 series either, because
Sorry, not only a 2,0 theory, but it's a leftover tensor multiplet. Let me say this.
Yeah. Like actually the base, like after you shrink all the curves, including the -2 or -3 curve, then the thing you get is a U2 orbifold of C2. Yeah. That's the difference. Oh, okay.
Sorry,
So,
one last question. So there's only very Higgsable and non-very Higgsable, or is there a third option?
No.
Okay, just these.
This definition is exclusive.
Non-very Higgsable, they divide in various options. One option is
that's why I. Yeah.
Okay. I think Nopadol is more familiar with this, but if I remember correctly. But I think the non-very Higgsable theories, they divide whether you can mix to a 2,0 theory or to like one of these 1,0 theory that have other self-intersection theory.
Okay, thank you.
Okay, so that was a notion about the 60 series. So now, if you want to go from the 60 1,0 series to a 5D SCFT, then we need to do a geometric transition to break the elliptic vibration structure. And that was already discussed by this paper by Fabio, Sakura, and me, and also papers by Dr. Bardwaj and their collaborators, Kammer and Rafa. And actually, for this particular case of C-series gamma orbifold, we define a T60 and T5D in the previous way. And this particular geometric transition we need to do is actually different depending on whether T60 is very Higgsable or not. So for the case where T60 is very Higgsable, then the geometric transition is simply by flopping a 2 cycle out of the bunch of compact 4 cycles. And physically, this corresponds to the decoupling of a 5D matter hypermultiplet. So a simple example would be the classical rank 1 E string case, where after you put it on a circle, and the 5D KK theory has an IR description of a SU2 plus 8 flavors. And then if you want to go to the T5D, you need to decouple one fundamental, and that goes to the Seiberg rank 1 E8 theory. Okay. And that's also precisely what we observed in this detailed, the actual singularity. And then when T60 is non-very fixable, then we need to decompactify a certain number of SIs, a compact 4 cycles. And physically, this corresponds to, so in 5D picture, this corresponds to decouple a number of UI vector multiplets. As an example, we start with this non-very fixable theory. All right, it's really hard to pronunciate. So this is just a G2 gauge group on a -2 curve, and we put it on a circle. Then we have to decompactify the vertical divisor over the -2 curve. And the new geometry will describe a rank 2 SCFT with IR description of G2 plus 4 flavors. So this was the introduction of the 60 SCFT and the relation to the 5D ones. So now let's talk about the detailed examples and the classifications of the finite subgroup gamma of SU3. So the simplest examples are just abelian cases, which include Zn and Dm times Zn. And besides that, we can also consider the non-abelian subgroup, finite subgroup of U2, which because U2 is a subgroup of SU3, so that's also a finite subgroup of SU3. But these are not the finite subgroup of SU2. Okay. The generator of this class B all takes the following block diagonal form. And besides that, we also have a type C, which includes a very important famous case of delta 3n squared. And that is a semi-product of Zn times Zn with another Z3 factor. Now, this is generated by a diagonal matrix and also a non-diagonal one. Okay, and there are also a few other set of examples as well. And then there's like a type D and so on, the exceptional subgroups as well. So now first, let's talk about the simplest cases, which are the abelian ones. In this case, whenever gamma is abelian, then the C3 mod gamma is always toric. And the resolution x tilde is simply given by the maximal triangulation of this toric diagram. And group theoretically is also pretty nice that for the abelian groups, each group element is a conjugacy class by itself. So it's also simplified. So let's take a most simple example, that's gamma equals to Z3. In fact, there are two different choices for the Z3 generator. The first one, it takes this form, 1/3 times 1, 1, 1. And so the only two non-trivial elements are this guy and this guy, the 2 times this guy. So actually, group theoretically is the square of this guy. But okay, and we can simply evaluate the h function, and you compute the h function. This guy has h1 and this guy has h2. So basically, it's the sets gamma 1 and gamma 2. Both of them have a single element. And now applying the formula I just introduced before, we can compute that the 5D rank of this guy equals to 1 and the flavor rank equals to 0. And this is exactly consistent with the fact that the C3 mod V3 should give rise to a Seiberg P0 series. So the geometry is just a local P2. Okay. On the other hand, we can also choose a second generator like this, but for these cases, and the geometry is actually C times C squared mod C3, and that does not give rise to a 5D series. So we will just ignore these possibilities. And the second very simple class of examples are the Tn theory, where gamma is Cn times Cn. So here I show the case with n equals to 5, and I just draw all the group elements, and each of them correspond to a conjugacy class, and they are organized in this square. So this one corresponds to this is like a periodic boundary condition, and this guy, and that guy are both, so they are all the identity element of Cn times Cn. Okay. So now I give a different color to a different element. So the blue guys correspond to the element with age function equals to 2, which will give rise to the compact 4 cycles. And the black ones are precisely the inverse element of the blue element. And this should give rise to the punctual dual of these 4 cycles. And finally, we still have 12 yellow nodes, which also has age function equals to 1. And this will precisely give rise to the Flavor symmetry of this 5D SCFT. And which turns out to be, when n is bigger than or equal than 4, these are the SUN cube. Okay. So this was the abelian cases, which are pretty simple. So now let's consider the non-abelian cases, which are more interesting. And for the delta 3n squared, this can also be thought as a Tn theory modeled by Z3, or the discrete gauging of the Tn theory by Z3, following the terminology of the paper by Bobby Acharya and the collaborators. So in this case, this C3 mod delta 3n squared has a pretty nice hypersurface equation form like this in 4 variables x, y, z, and w. And as you can see, in fact, in the coordinates x and y, this actually takes a Tate form, which means that this singularity can be embedded into a Weierstrass model, and we can also study the 60 SCFT interpretation as well. So let's take a few detailed examples. Question?
Do you know how this equation is computed?
So you write down all the invariant polynomials in terms of some so basically, let's see. So you can consider a 3-dimensional vector that's like x1z, xyz, and you consider the invariant polynomials in these three variables x, y, and z.
I understand. So you're saying you're computing,
and then you just try to write down the relation between these invariant polynomials. And in this particular case, there is only one independent relation, that is this equation.
So you find 4 invariants and one.
Yes.
Thank you. Yeah.
So let's talk about the simplest case n equals to 3, which is delta 27. So the 60 interpretation is pretty simple. It's just on the tensor branch, it's just a rank 1 E string, where there are 4 SU3 global symmetry factors attached here. And then as origin of the tensor branch, this Flavor symmetry should be enhanced to a bigger Flavor group E8. And then for the 5D interpretation, this is precisely the Seiberg rank 1 E8 theory. And that can be derived from the rank 1 E string by, refers to the compactification and then decouple a fundamental hyper. So that's consistent with the logic before. Okay. So a more non-trivial case is that of n equals to 4. In this case, the tensor branch picture is much more complicated and much more interesting. So in the 60 interpretation, after you go to the tensor branch, we have a single compact -1 curve. And on the -1 curve, there's a Caldera singular fiber of type I1. And this -1 curve also intersect 2 non-compact curves. And each of them carry a SU3 and SU4 gauge group, a Flavor, actually Flavor symmetry group. And another pretty interesting phenomenon is that the curves that carry an SU3 actually intersect the -1 curve non-transversally, and such that over the intersection point, the Caldera fiber is enhanced to type 4 instead of type I4. So now you want to ask this very important question, whether the theory is the same as a rank 1 E string or not. So a few years ago, Dave Martin and Tom Rudilius wrote this paper, which they kind of postulated that for an arbitrary type 1, I1 or type 2 fiber, quadratic singular fiber over a -1 curve, this is still the same as the rank 1 E string, because the positive evidence is that the maximal Flavor symmetry group you can have is still E8, not bigger than E8. However, we found a few like counter argument in this current paper, which show that the theory might be a different theory than the rank 1 E string. Well, the first argument is that if you try to embed this thing in a compact setup, such that the field theory is coupled to a gravity sector, then after you compute the contribution of this guy to the 60 gravitational anomaly, it turns out the contribution is bigger than that of the rank 1 E string. Now, this is simply because at this intersection point, there's some localized hypercharged matter under the flare symmetry SU4 over here. And after you shrink down the -1 curve to a point, you still have this extra contribution over this point, which makes the contribution to the gravitational anomaly bigger than 29. And as another geometric argument, it turns out that in the resolved elliptic Labial threefolds, the topology of the compact divisor is different from the elliptic rational surface as in the rank 1 E string case. This is because like what we mean by quadratic type I1 singular fiber. The I1 singular fiber means that it's an elliptic curve with a double point singularity. And that actually means that the geometric genus of this curve is equal to 0. And this new surface is very different from the smooth elliptic rational surface. And here I just draw all the the rational P1 curve on this singular surface as we know. As an additional argument, we also have this observation from the 5D picture as well, because in this case, the 60 theory is very fixable, and we expect that the relation between the 60 and 5D theories are simply by decoupling a single matter hypermultiplet. So let's talk about the 5D interpretation of the delta 48 singularity. So first, from the group theoretic computation, we can compute the 5D rank and flavor rank, so R equal to 1 and F equal to 5. So it's very suggestive that the theory is the same as the cyber rank 1 E5 theory because we have F equal to 5. However, the additional subtlety is that as in the previous 60 case, the single compact divisor after the resolution is also singular. And here I draw all the curves on the surfaces, and the C is actually a central curve of double point singularity. And now you may also wonder what is the flavor symmetry of this guy. And from the coordination 2 singularity, you can get a type A3 plus A2, which naively you may say that the flavor symmetry is just SU4 times SU3. However, because of the splitting of flavor curve, this effect I talked about before, so the central P1 curve of the type A3 singularity actually splits into two -1 curves like this, and they intersect at this curve C of double point singularity. And this is pretty complicated. And because of this splitting, the non-abelian factors of GF are actually SU2 squared times SU3, but not this bigger group. And as a consequence, the SU2 squared times SU3 times U1 can be embedded into the SO10 of the rank 1 cyber E5. Okay. So apart from this geometric computation, there's also another argument, a brainwave argument by this companion paper by Bobby and their collaborators, which they defined a brainweb construction, which is called the Z3 quotient of a T4 brainweb. And they also confirmed that this series should be a cyber rank 1 E5 series. Nonetheless, as another side comment, there has been a recent paper by Kim and Lee at the end of last year, which they say that the C3 quotient of the T4 brainweb should be the cyber EA theory. However, I thought that these two different notions of C3 quotient is actually different in these two different papers. So up to now, we still think the series is still a rank 1 E5. Okay, is there any question at this point? Okay,
yes.
yes.
All the data delta 3n squared can be computed by a Z3 quotient of this Tn theory.
I think so, but actually, in their paper, they only study the n equals to 3 and n equals to 4 in a detailed way. I don't really know why, because it seems like it should be possible to do this in general.
I see. Okay. And is there a similar construction for 6n squared?
I don't know.
I see. I see. And do you also know what kind of computations did the Kim Lee do when suggesting this?
It seems that for the Z3 quotient, they actually introduced an E6 monodromy as the origin. So instead of the SU3, so in this paper, so in order to materialize this Z3 quotient, they introduce like a SU3 or Caldera type I3 type monodromy as the origin. In addition to the T4 brainweb component, but in the Kim Lee paper, they use the E6 monodromy rather than SU3. I think this is a difference.
I see. Okay. Thank you.
So I think my time is kind of over already. So I will just show. Yeah, Julius.
Go on. I mean, for me, you can continue a bit.
Okay. So I will just show a few examples, like the delta 3n squared n equals to higher 3k, and we write down the 6D interpretation and the 5D interpretation as well. And as you can see, when k grows, actually the 5D rank grows pretty quickly. And finally, we in this talk, I also show an example, the delta 6n squared. Here n is an odd number. In this case, the singular equation is a computer section of 5 complex variables and 2 equations. And in this case, actually, as you can see in this form, the first equation also takes a form of a Weierstrass model. So it's a cubic equation in x and y. And the base variables on UV are UV and W. However, this UV W satisfy an additional relation that's the second equation. The 6D interpretation of this thing is that the base B2 will have a Z2 orbifold singularity after you blow down everything. So, or in other words, this is a non-verifiable theory. So here I just draw the 6D interpretation on the tensor branch, which is a G2 over a -2 curve that I already talked about in the earlier part of this talk. And the 5D interpretation is precisely obtained by decoupling a vertical divisor over the -2 curve, and you get this rank 2 5D SCFT. Okay. So now let's briefly summarize this talk. So in this work, we studied the C3 Mckay orbifold, which forms a large class of canonical threefold singularities, and we can easily study read off r, little f, the higher form symmetry, and the condition to ADE types from the gamma itself. And for certain cases, there exists a 60 companion, 60 SCFT description as well, which is related to the 5D description via either type 1 or type 2 geometric transition. And in the future, there are a few important things. The first one is that from the 3D Mckay correspondence, in all of the cases, the resolved Claviel threefold has a B3 equal to 0 and no terminal singularity. Now then follow a recent conjecture by Cyril, Simone, Sakura, and me. This thing should give rise to a so-called good magnetic quiver in the Higgs branch description. However, up to now, we still don't have any clue like how to study the deformation of the singularity, nor how to like systematically study the Higgs branch via brainweb. And of course, it would be interesting to generally understand the physics of the singular compact four cycles, and whether the 60 series that I mentioned before are really new series or not. Okay, so that's conclude the talk, and thank you very much.
Right, let's thank Yi-Nan. Do we have more questions? So I can ask a canonical one, but I think it was already asked a bit before, but which of the theories you discussed today have a brainweb description?
A brainweb description.
Easy way to say which one has one?
Yeah, sure. So the abelian ones are toric, so they have a brainweb.
Sure.
Sure. Yeah, and also delta 3n squared as in their paper.
Okay.
And that's the only cases that we know.
I see.
There's still plenty of things that to be explored. Yeah.
Is there any reason to think that there may just not be a brainweb, like that there's no generalized toric way to write down?
Well,
thoughts on this?
Yeah. So it's just because that in general we don't have a map from the singularity to the GTP yet. So that I don't know.
If you can construct it as an abelian theory with an additional discrete action, then you're good. So there is a challenge now to find some representation for 6n squared.
Yeah, maybe. I don't know.
There is
it seems like you can take the reflection of the delta 3n squared, but I'm not sure.
There is a paper by Tomomi Muto, which does try to write down a brain description for 6n squared, and he was doing it in the context of brains and singularities.
Sorry?
I couldn't hear you, Ami.
Yeah.
He was doing it for in the context of brains on singularities, which actually Mckay is still around. I mean, there is a question, a general question regarding the brain. So if you take a three brain probing the same singularity compared to the 5D theory, Mckay came up with the statement that the two theories are related to each other. One is a BPS quiver of the other. And I'm just wondering if this thing will persist in these cases as well. There is Mckay.
Hey. Yes, indeed.
You think that's going to persist?
Yes, that's the thing that we wrote in this paper with Jonathan also.
I see. Okay.
And that's the way. That's in a sense that's the physical reason why you can read off the one form symmetry and from the quiver, because the quiver is captured by the Dirac pairing, and the Dirac pairing is the object that physically captures the screening of 't Hooft.
I see.
So yes, it's precisely that. the Mckay, the Mckay quiver of C3 mod gamma is a version of the 5 dBps quiver that we discussed also with Cyril.
I see.
And there are also, I mean, these applications of these orbifold singularities, which we found with Jonathan and Morrison back in the day when we started looking at the reduction from 60 to 5D, which are where also we found applications of these orbifold singularities in the reconstruction of higher dimensional 6D theories. But yes, this is I think that this is the right that's the interpretation.
Yeah, I see. Now, also
a remark that we had with Cyril and Stefano in an ongoing project, which also involves Francesco Carta and some students in Durham, was that if you look at the index of this 4D theories, these are 4D CFTs, the 4D CFT on the little brain, which is also building on something that you have done with Sergio, I think. The index somehow knows about the flavor symmetry, right?
Yeah,
so you mean the 5D flavor symmetry?
The index of the 4D theory knows about the global symmetry of the 5D theory.
Oh, I see. That's
in a weird way. Yes, this is a remark that we had with Cyril and in an ongoing project.
I see.
Which might be a way of reading off the flavor symmetry indirectly. I mean, because in these cases it's not always manifest in geometry.
Yes, that's right. Yeah.
So in the case of Z3 cross Z3, the 4D gauge theory is this 9 gauge group periodic theory, and you compute the index for this. And somehow it reveals some E6. Exactly.
And it is not a global symmetry of that theory itself, but because you don't have an E6 current, but you get E6 characters all over the place.
I see. Yes, this reminds me some work we did with Sebastian back. We were trying to.
Yes.
You've seen that? You've seen this one? Yeah.
Yes.
But we didn't compute indices back then, and there was no clear way of continuing this. The motivation came in an attempt to compute the superpotential for those theories. I see.
Yeah, that's the hard part. It's very hard for Cyril came up with an argument for computing the superpotential. Yes.
I see.
But it's very hard in general. We are going slow because for exceptional groups it becomes very hard. For E7, E8 is very hard. So we know it for the orbifold points, but if you go away from the orbifold, then the superpotential gets deformed. And
another thing I want to raise is this name, very Higgsable, non-very Higgsable. I just don't understand the motivation for those names.
So can we just clarify for me now, what are the different cases? So very Higgsable means that you can completely break everything. And non-very Higgsable, you have a choice of whether there is a 1,0 or 2,0 left behind. This is what I gathered now, but is this the statement?
Well, yeah, kind of. But I mean, the actual difference is just that as an origin of the tensor branch, whether the base is a smooth base C2 or a singular base with some kind of orbifold singularity or not. Yeah, that's the difference geometrically. So physically,
it's a geometric distinction and not a theoretical distinction.
Field theoretically, this is like.
I think I disagree. It's a field theoretic distinction, and the first instance where it appeared, it was in this UG paper where it discussed 6D compactification on T2 back in
14
14 something.
But the gauge theory doesn't know about those notions of Higgsing and non-Higgsing. If you talk about Higgs mechanism, that's fine, but it seems like it's beyond that. So why do you say it's field theoretic?
With field theoretic, I mean that one theory can be X to 3 hypers and the other one cannot be X to 3 hypers. That's what I mean by field theoretic.
Yes.
I think it's also like a SCFT statement more than a HDF.
So give me when you say X to 3 hypers, this is a very dangerous comment. Are you really sure that the Higgs function is a collection of 3 hypers? That's probably not correct.
No, I'm not saying that the theory can be X'd completely to 3 hypers.
But I mean, the 60, there's also still the tensor. If you so because this geometric transition is not only a Higgsing anyway.
Okay, so you seem to disagree. You're using the geometric picture, and there is this.
Maybe we can discuss more in a moment and see if we have any last questions for Yi-Nan on his orbifolds. If there are no pressing questions, I would say let's thank him again.
Thank you.
Recording.